Section 11.4, limits at infinity and limits of sequences. So we're going to evaluate limits of functions at infinity and find limits of sequences as well. The first thing I want to look at is what's the limit of the function x plus 1 divided by 2x where x is going to infinity. Pause the video for a second and see if you can use the table in your graphing calculator, graph this, and see if you can figure out what that answer is. All right, as you tried to do that, you got a graph that looks similar to what I have here. You also might have looked at the table and made x really large to see what it was approaching. But if you think about this as a rational function, we have a vertical asymptote where x is undefined at x equals 0. We have a horizontal asymptote where those two parts of the graph approach as x goes to negative infinity and as x goes to infinity. So think about that. As x gets larger and goes to infinity, what is the y value getting closer and closer to? Well, it is getting closer and closer to that horizontal asymptote. So what is the horizontal asymptote of this function? Well, remember, it has to do with your degrees. If the degree of the numerator is the same as the degree of the denominator, then you take your leading coefficients, and this horizontal asymptote would be at 1/2. So therefore, the limit as x goes to infinity of this function would be equal to 1/2. So when we're looking at limits of infinity, we're going to be looking at some rational functions here, and if you know what that horizontal asymptote is, then you're going to know what the limit is. So let's take a look at a couple examples here. Find the limit as x approaches infinity of all three of these functions. Now they all look very similar, but we're going to pay attention to the degrees. So the degree of the top is 1, the degree of the numerator, the degree of the numerator is 1, the degree of the denominator is 2. So what is true when you have the degree that is smaller in the numerator than the denominator? So when the numerator degree is less than the denominator degree, you have a horizontal asymptote at y equals 0. So therefore the limit as x goes to infinity is at 0. The next one, your degrees, as we just spoke about, are equivalent. They are equal. So when your numerator degree is equal to your denominator degree, then your horizontal asymptote is the leading coefficients of those terms. So in this case, that would be -2/3. And then on the last one, we have the numerator as 3 and the denominator as 2. So your numerator is greater than your denominator, and that means there is no horizontal asymptote. So if there's no horizontal asymptote, I'd have to graph and see what this one looks like. But if there's no horizontal asymptote, then this graph is going to increase or decrease without bound, so therefore this limit does not exist. Okay, because once again it's going to approach infinity. So that's how we look at limits at infinity. Take a look at example 2. I want you to try these 3 on your own. So pause the video. I'm going to work through them and then unpause and see if you got your answers correct. All right, on the first one, you need to simplify the numerator. So we multiplied 5x times x minus 3 to get 5x squared minus 15x. So your degree is 2 over 1, so therefore there is no horizontal asymptote, so the limit does not exist. On the next one, the degree in the numerator is 3 and the denominator is 4, so therefore the horizontal asymptote is at y equals 0. So as x gets really large, it's going to approach the horizontal asymptote at 0. And then the last one, the degrees are the same. So you take the leading coefficient, -6 divided by 3 is -2. So the next part is looking at limits of a sequence. So a sub n is equal to 1 over 2 raised to the nth power. If you expand this out in terms of, the first term, second term, and so on, this would equal 1 over 2 raised to the first power, then it'd be 1 over 2 to the second, 1 over 2 to the third, 1 over 2 to the fourth, and so on. Okay, so what is going on? Well, you got 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. The denominator is getting larger and larger and larger, but the numerator is staying 1. So what is that number getting closer and closer and closer to? So as n goes to infinity, as that term, continues to get larger and larger and larger, your fraction continues to get smaller, smaller, and smaller. And so what value is it approaching? It's approaching 0. So the limit of the sequence 1 over 2 raised to the n power is equal to 0 when n is approaching infinity. So what is this? The sequence is said to what we call converge. So if it converges as n increases without bound, so n is going to increase without bound, it means go to infinity, the terms of this sequence get closer and closer to 0. And that's, one way just looking at a sequence and being able to try to find the limit of that sequence is just to look at the pattern and look at the terms and see if you can identify where it's going and what is it getting closer. Let's look at another sequence here. The sequence is -1 raised to the n power. So we want to know what the limit is as n goes to infinity. So if you look at the terms, -1 to the first power would be -1. -1 to the second power is 1. -1 to the third. -1 to the fourth. -1 to the fifth, and so on. What's going on? Well, it's going back and forth between -1 and 1. So as n goes to infinity, is this number getting closer to anything? And obviously it's not. It's just going back and forth. So this sequence, we say it's not converging, but it's diverging. Okay, it's not approaching anything. So on example 5, what we want to look at is I want you to list the first 5 elements of the sequence. One, just to kind of see if you can recognize what that pattern is, but then we're going to determine the limit, if it exists, of the sequence itself. So I'm writing it in limit form, so limit as n approaches infinity. The sequence that we're looking at is right there. So 2n plus 1 divided by n plus 4. So the first thing is, you can do this just by plugging in n equals 1, because that's what we're going to start with. We'll always start with n equals 1. That's your first term. So if you plug 1 in, you'll get 2 plus 1 is 3, and then 1 plus 4 is 5. So I'm just going to write these out, but you're plugging in 1. The next one you're going to plug in 2. You get 5, 6. The next one, when you plug in 3, you're going to get 7 over 7, which is 1. And then we're just going to continue it out to 5 total elements. So the last one would be 11 over 9. So if you look at this, you got 3/5, 5, 6, 1. So it's getting larger. It gets to 1. Now it's 9/8, 11/9. It's still getting larger. But do we really know just by looking at the first 5 terms, when we're trying to look at n goes to infinity, do we know what it's approaching? I think that's a little bit difficult to do to determine in the first 5 elements of the sequence. So is there another way we can figure out what the limit is? Well, if you look at the expression, it's written as a rational expression. So we can use the idea of what we used earlier in terms of the degrees. So the degree of the top is 1, the degree of the bottom is 1. So what is this number getting closer and closer to, that horizontal asymptote again? So in this case, the degrees are the same, so the limit would approach 2 over 1, which is just 2. So these numbers, and you can plug in n equals 100, and n equals, any large number there, and you'll see that these numbers will get closer and closer to that value of 2. So let's go ahead and look at B. So once again, as n approaches infinity, we've got 2n divided by n squared plus 4. So I'm just going to write here what these next 5 terms are. So if you plug in 1, you'll get 2 over 5. If you plug in 2, you're going to get 1/2, 3, 16/13, 4, 2/5, and 5, 10/29. Once again, just to find the sequence in terms of what those first 5 elements are, all we're doing is starting with n equaling 1 and then going from there. So once again, as you look at the sequence, 2/5, 1/2, 6/13, 2/5, and 10/29, what is this number getting closer and closer to? Very hard and difficult to be able to see that. So we do, what we did a second ago is that we look at the degrees. So the degree on top is 1, the degree on bottom is 2, so therefore the horizontal asymptote of this rational expression is going to be y equals 0. So therefore the limit as n goes to infinity, it has to be going to infinity for us to determine that. As n goes to infinity, it will approach 0. Alright, try the last one on your own. And so the last one, your first 5 terms or elements are 1/2, 5/16, 5/18, 17/64, and 13 over 50. What is the horizontal asymptote? What is that n behavior? Well, as n gets really, really large, the horizontal asymptote is at 1/4, so the n behavior as the limit of that expression as n goes to infinity will approach the value 1/4. All right, and the last example I wanted to look at is find the limit of the sequence whose nth term is that. Okay, that's what the expression represents. So we're trying to find the limit as that approaches, as n approaches infinity, as this term gets really, really large. What is it approaching? What is this sequence approaching? So to do this, we really just need to simplify it. So take that expression, simplify it, and then we'll take a look and see if we can identify what that horizontal asymptote is, so we know what the limit of the sequence is going to be. So pause the video once again, work through this one, and see if you can figure out what that horizontal asymptote is, so we can find the limit. So I've taken that expression, I've simplified all the way down. I could have canceled some common factors, but since I'm looking at the n behavior as n gets really, really large, I don't necessarily need to cancel those out. I really just want to focus on what that horizontal asymptote is. And since the degrees are the same, then I'm going to take my leading coefficient, and we need to write this correctly. We want to say the limit as n approaches infinity of the sequence a sub n, that is equal to 16 over 6, which reduces to 8/3. So here's your leading coefficients. 16 divided by 6 reduces to 8/3. So that's the limit of the sequence. So that is it for limits. So go ahead and create your summary, really looking at limits of infinity and how we're going to be looking at the horizontal asymptote or the n behavior, but then also limits of sequences as well. And if sequences are written as rational expressions, then we can use the n behavior for those as well.